So now we're looking at pipes or hollow tubes. We can set up stationary waves inside these just like we have seen them for strings, and in fact what happens with a pipe is that you get two travelling waves meeting. One is the reflected wave from the end of the pipe, either the open end or the closed end, both will reflect, and when the reflected wave superimposes with the other travelling wave, a standing wave can be set up. Only those waves that fit the length of the pipe will become reinforced and form these standing waves. So in this diagram we see the fundamental for a closed pipe. You can see this end here is closed while this end is open. You can see we get an antinode at the open end and we get a node formed at the closed end. And if you look carefully at the shape of this wave, it's only a quarter of a wavelength for the fundamental. We double that for the second harmonic, F2, and so in fact we get we don't get double, we get triple. The second harmonic as such, if it were to exist, would finish on this dotted line here on a node at the open end, so that's why we don't get the second harmonic as such for the closed pipe. So we need to go an extra quarter wavelength to get this antinode forming, so then we can hear this particular harmonic. So notice this is now 3/4, where that's a quarter of a wavelength, this is a half and another quarter. So 3/4 of a wavelength fit into this pipe for the second audible harmonic. And then the next one in the series has to be 1, 2, 3, 4, 5/4 of a wavelength. So that's the pattern we're going to look at in the generally next. On the other hand, this is the series of harmonics possible for an open pipe at both ends. So in this case we get antinodes forming at the open ends of the pipe and nodes in the middle. The first harmonic, you can see the length of the pipe is exactly half a wavelength. For the second harmonic, it's a bit more than that. It's in fact one wavelength, isn't it? One wavelength for the second, and then for the third, it's starting here, it's 1.5. Now those diagrams show the stationary waves for those harmonics. Just to remember that they are not actually transverse waves. They're all longitudinal stationary waves because they're sound waves. The diagrams, however, they are giving a graphical representation of the waves which look transverse, but just remember that these are in fact not transverse in reality, they are longitudinal in nature. The reason we do that is it's very hard to draw a longitudinal wave, so the graphical representation preferred is the transverse shape. Same physics applies for the equations. For the fundamental frequency of the closed pipe, as we saw earlier, the length of the pipe L is a quarter of a wavelength, and when you want to find the next possible harmonic, you can only use odd numbers for n in this equation here. Like I mentioned, number 2 and number 4 and so on do not exist because of the nature of the shape of the wave formed. You get a node at the open end, which means no sound is actually heard. For the open pipe, the length of the pipe is equal to half a wavelength, and the general formula, you can use any number for this equation for n. For the nth harmonic, it's 2L upon n. Now you could calculate the frequency of any particular harmonic n simply by using the wave equation, as we've seen earlier with the strings. depending on which pipe, you would get a slightly different formula resulting. This is just a small note about diffraction, because it does lead into understanding interference patterns. So what is diffraction? It's basically the spreading out of the wave when it meets an edge or a barrier or a slit inside a barrier, like a big open hole, for example a harbour entrance. When the ocean waves come in to a harbour entrance, they tend to curve and bend. Basically they don't travel in straight lines, but they bend around the edge of the slit. The extent of the bending depends upon the relative sizes of the wavelength of the waves and the size of the gap or the dimensions of the slit. So here's a diagram showing this effect. You can see the gap between successive crests on the left hand side. This gap here is the wavelength, and notice the size of this gap here is similar to that wavelength size. So we get plenty of wave spread or curve or bending on the other side. However, in the second diagram you can see that this gap size is much bigger than the wavelength, so the amount of spread we get is pretty minimal.